So much better. Hi, everyone. Good afternoon. Glad to see you guys here. Sorry I was a moment late. I could not get in the system. It kept telling me that live stream wasn't available, so I had to shut down and come back in. So I hope you guys had a great day. Today's class is not going to be long at all. We're going to go over activity 83, 84, and 86. I won't go over until Monday. And then I have a couple other things I want to go over with you just to make sure you understand those concepts. So if you can just kind of, say hi or something, if you can hear me, that would be great. Can you guys hear me? Hi, awesome. That is awesome. Okay. All right, folks. So we're going to go over activity 83, coming to a stop. And then I'm going to discuss a couple of things in regards to your upcoming test. And then we'll be done for the day. And as you know, we don't have class on Fridays, so I won't see you again until Monday. So really quick, I just want to verify that those of you who may not have been here yesterday or are listening to this didn't hear yesterday's broadcast, please make sure you check to see if you have any assignments that are not complete. I'm referring to older assignments, and make sure you get those in. Okay, I want to give you guys every opportunity to do well. Even if it has a 0 in it, it doesn't mean you can't turn it in. It's just showing you, listen, if you don't do your work, this is what's going to happen. Okay, so any questions, feel free to let me know. Send me an EDSB message. Those of you who've been vigilant on EDSB, who turned in old assignments, you'll see that, okay, HP is trying to give me grief in the middle of a live chat. Okay, you'll be able to see that we were, that I've been grading assignments. I haven't graded in about the last hour, obviously, because I had to get ready for class, but I did grade this morning. So I would have to say almost everything is graded. If anything was turned in the last hour, that would be the only exception. So hello. So, all right. First question is, why does stopping distance depend on road conditions? Okay. What is one of the big reasons stopping distance depends on road conditions? Let's start with that. Anyone have any idea? I know it takes a moment to type. Friction can vary, and with friction varying, stopping distance varies. That is absolutely correct. So as you have an increase in friction, or a slippery road can raise the distance required to brake. That is correct. A slippery road raises the distance required because as your car is sliding, it takes you longer to come to a complete stop. Great. Number 2, what might cause slippery road conditions? If the road is slippery, you won't have as much traction than you would if the road is dry. That is absolutely correct. Okay, rain can cause a slippery road. Anyone else? Snow. Snow, which at a certain temperature freezes. Snow is a solid form of rain, but ice. That is correct. So snow, if it mixes with moisture, particularly if you have those conditions where it's a little bit warmer during the day and then it's below freezing at night. So anything that, any moisture has not frozen into solid ice. Black ice, yes, very dangerous. Okay, anyone from up north probably knows that all too well. Okay, creates a very dangerous situation on the road. So, but there are some other things too. Okay, what is one thing that cars tend to give off in very small amounts, sometimes more than others because there's a problem with the vehicle, that when mixed with water can cause a really dangerous situation? Black ice is ice that is not noticeable on the road. So if you're walking or driving, that is correct, Andrea Oil. I'm going to get back to that in just 1 second. Black ice, if you're driving, and it's not necessarily just on a road, it could be on a sidewalk as well. So it is not visible to the naked eye very easily, which makes it even more dangerous because as you're driving, your car will actually go skidding. I actually not fractured, but I actually tore 3 ligaments in my ankle due to black ice. It was in a driveway, and as I was walking, my legs slipped out from under me and my foot went the wrong way. Again, it's not noticeable on the ground. And unfortunately, it creates a very low friction surface that can cause someone to get hurt. So, so question number 2 was, okay, oil. We were talking about oil. So when your car releases oil, it releases some transmission fluid, it releases some motor oil, even in small amounts, even in like a mist, it'll settle to the ground. And you're talking about hundreds, if not thousands of cars passing roadways on a daily basis. That tends to accumulate. It'll usually accumulate in the cracks in the surface of the road. It'll accumulate in your tires. And what winds up happening is when it rains, that stuff, the water will go under it. You know the relationship between oil and water. The oil will come up above the water and it'll sit on the surface of the road. And when your tire comes into contact with it, it skids. So it actually reduces the coefficient of friction of the road. Okay, so these are all things that can cause slippery road conditions. Too much water on the road. Hydroplaning. I don't know if any of you have heard of hydroplaning, but basically the water creates a surface between the tire and the road so that the tire is not sitting on the roadway anymore, but rather it's sitting on top of a thin layer of water. So when you go to brake, well, the car's not going to brake. It's going to go skidding. And hopefully, as it slows down a little bit more, gravity takes a little bit more effect and you'll actually be able to get some traction, but it increases your braking distance a great deal. Very unpleasant situation. Scary as well. What about driver distractions? A lot of people said the exact same distraction. I'm sure you can guess what it is. What is the main driver distraction? And can you think of any other distractions? Cell phones, electronics, that is correct. Any other ideas? Music, that is correct. Music. Anything else? Okay, changing music, texting, billboards. So your external environment, that is actually true. People will start reading billboards and they're not paying attention to the road. Okay, people around you. Anything that causes rubbernecking, even an accident on the side of the road. Now, that sounds very strange, but how many of you have ever been in a car and you or another driver, you could be sitting in the passenger seat, but maybe the person driving the car that you're in, or maybe you see someone else in another car and they're doing this and they're not paying attention to the road. Okay. Driving while drunk, it actually reduces your reaction time. Okay. Squirrels, that's kind of funny, but true, especially when they cut in front of you and you're trying not to hurt them. Okay. Advertisements. Left out a big one. Children in the back. I was in a car accident in high school like that. My coach was driving, God rest her soul. She was driving and her son was crying incessantly and she went to turn around and wound up hitting the car in front of her while we were on our way to a track meet. So I really hope there are no children in your trunk. So, but yeah, anything in the trunk that's not supposed to be in there, that is true. Food and drink. Eating while you're driving reduces your reaction time. Eating while you're driving, eating while or drinking. And now what I mean drinking, I don't mean drinking alcohol. I mean having a bottle that you have to take a top off of, having any kind of beverage, coffee, all of these will actually reduce your reaction time because you're splitting your focus between driving and eating. Okay. So squirrels always make a run for it when my family is in a rush. I can't tell you how many times critters have run in front of my car. It's just really annoying. Raccoons, squirrels, and I'm sure you've noticed all the roadkill because we have so much wildlife in Florida. I'm sure you've noticed all the roadkill, you know, possums, cats, sadly, sometimes even, you know, cats and dogs always break my heart. Raccoons, the works. Okay, I don't know where you would find a rhino in Florida or what rhinos would be doing on a road, but okay, deer, yes. Okay, now you guys are getting crazy. You're not going to find a tiger in the middle of the road in Florida, I'm just saying. So, unless the cat sanctuary somehow let all of its large cats loose, I don't think you're going to find any big cats. Okay, so in which of the three situations? So there are three situations we're going to look at. An alert driver on a dry road, a distracted driver on a dry road, and an alert driver but on a slippery road. Which one is actually going to take the least distance to stop? In other words, their braking distance is the shortest. What's going to take the least distance to stop? The alert driver on a dry road, that is correct. What's going to take the greatest distance to stop? And this could be debatable. That is a great answer. Depending on your speed, it will change. Well, we don't have distracted and slippery in this case. We have distracted on a dry road and alert on a slippery road. In this case, it does depend on the speed. Usually the distracted driver on the slippery road is going to have the greatest stopping distance. And the reason for that is because an alert driver, whether they're on a slippery road or a dry road, they're focusing on what's going on. And because they're focusing on what's going on, they'll initiate the stop quickly. But if you're distracted, you could be on your cell phone, you could be foraging for something, you could be eating. And so you're not paying attention to what's going on in front of you. So you're not actually taking the time to initiate the stop. And because you're not taking the time to initiate the stop, you've lost a great deal of stopping distance, you know, between when it should have been initiated and when you're ending. Okay, so now if the alert driver on the slippery road is going really fast, now you're in a situation where that may extend the stopping distance because of the fact that speed extends your stopping distance as well on an exponential factor. Okay, so you are alert and driving at 40 miles per hour. You come around a bend and see that a tree has fallen across the road 50 meters away. Will you be able to stop before you hit the tree on a dry road? Yes or no? Yes. You'd be close, but you would stop in time. That is correct. What about on a wet road? Would you be able to stop in time? On a wet road, you're not stopping, because you would stop on the dry road. If you had looked at the distances on the graph that I gave you, on the dry road, you would stop 4 meters from the tree. On a wet road, you would need 81 meters. You're 31 meters short of what you need to stop. You'd actually would hit the tree. Okay, now, would your answers to number 4 change if something was distracting your attention as you came around the bend? So your cell phone rang, your drink spilled, you're trying to go digging for food, your kid said something to you and you turned around to see what it is. So now that you're distracted, is your answer going to change? Yes. Okay, so if you were distracted, it would take 73 meters to stop in dry conditions, 23 meters short of 23 meters longer than the distance the tree is from you when you come around that bend. So you're going to hit that tree. Now, if you were driving 20 miles per hour instead of 40 miles per hour, so now you are in dry conditions, but you're not driving 40 miles per hour anymore, you're driving 20 miles per hour, would you be able to stop in dry or wet conditions? You'd stop for both. In dry conditions, you would need 18 meters to stop, so you've got a lot of space between you and that tree. In wet conditions, if you're driving at 20 miles per hour, you would need 27 meters to stop. The tree is 50 meters away. You would definitely make it. Okay, great. Number 4, your friend says that when a car goes twice as fast, its braking distance doubles. Do you agree or disagree? And what evidence do you have for that? Okay, you're saying your reaction time stays the same. Anyone else? If you look at the graph, you disagree because according to the table in the chart, the distance does more than double. That is correct. And I was actually looking for the chart, which I didn't put back in here, but I do have the table. If you look at, and the question specifically states, if you go twice as fast, does your braking distance double? If you're going twice as fast, let's say from 4.5 meters to 9 meters, your braking distance on an alert driver on a dry road or an alert driver on a slippery road, your braking distance goes from 3 to 14 meters. On a dry road, it goes from 1 to 5 meters. So it is not doubling. It is more than quadrupling. So you have actually an exponential factor. So if you look at the graph, it's not linear, it's exponential. Okay, you have a curve. So it increases quite a bit. So does anyone have any questions? In the meantime, I'm actually going to go over some concepts I want to go over with you in regards to your test, some concepts that we may not have discussed. So let's say I have a book, right? And in order for you to see the book, it would have to be on a flat surface, but I would have to keep moving the camera. But if I took the book and I pushed the book, okay, and I'm applying a constant force, right? Now let's say I added a second book and I applied a constant force. What would happen to the acceleration of the books if the force remained constant? So we're comparing one book with a force, and I'm pushing it so the book is moving. And then I now have two books, and I'm applying the exact same force, and the book is moving, or both books are moving. What would happen to the acceleration of the books? Are the books going to move faster? Is the speed at which the book's moving going to stay the same, or is it going to move slower? No one's got an opinion? It's going to move slower. That is correct. So the book's acceleration is going to be less, because if I'm applying the same force, but I'm moving a greater mass, then the acceleration is going to be less. Okay? Does everybody understand that? So let me just go ahead and explain it this way. If I have a force, let's say force 1 is equal to mass 1, acceleration 1. If I keep force 1, so force 1 is the same, but I have mass 2, and mass 2 is greater, then acceleration 2 would have to be less for them to equal to force 2. For example, Kip, why do you disagree? Okay, so let me give it to you in terms of numbers. Okay, so we're going to say force 1 is equal to 10 newtons. And I'm going to use really basic and simple numbers. Force 2 is equal to 10 newtons, right? So if the mass of the first substance is 1 kilogram, in order for the force to be 10 newtons, it would have to be multiplied by 10 meters per second squared to have a force of 10 newtons, because 1 times 10 is 10, correct? But then, if I increase my mass to, let's say, 2 kilograms, in order to use the same force to push this 2 kilogram mass, it is now only going to move at a rate of 5 meters per second squared. So 1 kilogram pushed at 10 newtons would travel 10 meters per second. 2 kilograms pushed at still 10 newtons would only move 5 meters per second. Does that make sense? Are we good? Does that make sense? Does anyone need another example? Okay. All right, so that was one concept I wanted to go over. Okay. So you are working at, let's say, a new car company, okay? Burns Motors. And you guys have created a whole line of cars, but you want to test the safety features on the cars, okay? And what you are testing is to see which car is going to hit the wall with more force. Now, both cars have two completely, or they're going to the wall at the same speed. Oh, I'm sorry. I apologize. I was thinking something completely different. One car is an SUV, a big one, and the other car is kind of like a smart car. It's teeny tiny, okay? In order to test which one is going to hit the wall with greater force, are you going to be driving it at the same speed or different speeds, and why? So again, we have a car that's really big, like a Ford Expedition big, and we have another car that's really small, like a smart car small. And we're testing to see which one is going to hit the wall with more force. If it's going to hit the wall with more force, which one is going to hit? What are we going to do in terms of speed? Are we going to drive the same speed, different speeds, and why? And Rosie, when you say you want another example, do you want another example of this that I did before? Okay, so as soon as we're done with this example, I'll go back and I'll cover that. Okay, we're going to do it at the same speed. And the reason we're going to do it at the same speed is because if we're testing one variable, which is the force of impact, if you change the mass of the cars, you have to keep the speed constant. Otherwise, you're not going to know if the force it hit was a result of the mass or was a result of the speed. Does that make sense? Because we know mass impacts force changes and we know speed impacts force changes. So in that particular case, if force changes are impacted by both speed and mass, you have to keep one constant when you're changing the other. Okay, Rosie, I'm going to go back to the example. Let's say you're at Publix. Okay, so you've got your shopping cart and you're at the beginning of your shopping expedition, and you are pushing that cart with a constant force. You're applying the same amount of force on the cart to push it towards your destination. Well, now you've done your whole shopping, and now this empty cart is now full. But you're still putting the same amount of energy behind the cart. You're still pushing it with the same force. Are you going to move faster or slower as you move to the cash register? Faster or slower? The amount of energy we're putting into pushing it is exactly the same. It's going to move slower. You are correct, Aaron. And the reason for that is because if you're keeping the amount of energy going into it constant, if you're keeping the force behind it constant, then what's going to happen is as the mass of it increases, the slower it's going to move. If you want to keep it going at the same speed, you're going to have to put more force behind it. Okay? So to go over this a little bit more, remember force, and I'll put it up here, force is a product of mass and acceleration. How much material you're dealing with, how fast it's moving. So in order to, that's the reason why if you're driving a vehicle, okay, a lot of people talk about horsepower, engine power, and this is something that we talked about when we were discussing how fast a car was moving and its horsepower in the vehicle. So when we were discussing horsepower, we talked about how some cars don't need as much horsepower as other vehicles in order to move. Okay. The reason for that is because if you have a big sand truck that's full of sand, if you want that sand truck to move at, let's say, 70 miles per hour, it's going to need a lot more horsepower in that truck than, Toyota Camry to move to 70 miles per hour. And the reason for that is because not only does it have to move that speed, but it has to overcome all the mass associated with it to move that speed. Well, a Toyota Camry has a lot less weight than a sand truck full of sand. A sand truck full of sand's got a lot more matter. It's got a lot more mass. It's going to take a lot more force to push it to go the same speed. Okay, same thing with the shopping cart. In order to push a shopping cart through the store, once it starts getting heavy, once you start filling it, you have to put a lot more energy behind it. You have to push it a lot harder in order for it to continue to move at the same rate. Okay, same kind of concept. So if you look at over here, if you're pushing a 1 kilogram force, it's only going to move 10 meters. It's going to move 10 meters per, and you're moving it at a rate of 10 meters per second. You're going to have 10 newtons. But if you double the mass, you're only going to move half as fast if you're applying the same force. If you want it to still move at 10 meters per second, well, now you're going to have to double your force. Does that make sense? Okay, because in order for you to be able to maintain the same speed with a greater mass, you're going to have to increase the amount of force you put behind it. Okay? Questions? Okay. I know some of you guys are bored at home. And once you get your schoolwork done, you're very welcome, Rosie. You guys don't have much left that you can do, especially if you're not video games inclined, but, get creative. Draw, read, write. And when I mean write, I mean write something that's interesting to you. Make up a story. Take your pets out to the yard and play. Okay, it's, there's only so much TV you can watch, but, it's just a lot. It's a lot to get stuck inside over and over, but get creative. Go for a walk. Just make sure you go for a walk at a time that there are not a lot of people outside, and stay far away from anyone you run into. So, does anyone have any questions on anything that we're doing? Let me see if there's anything else I want to go over right this minute. Okay, so you have a brick that's sitting on a table, okay, a block. And this block is being pushed in such a way that it's moving very slowly. So let's look at my bottle here. Oh, I thought, okay. Let's look at my bottle here. Okay, and I'm pushing it in such a way that it is moving very slowly. What forces are acting on my bottle? Think of every force that's acting on that bottle as I'm pushing it very slowly. You don't have to name all of them. You could name one. So I'm pushing it very slowly across the book. What forces are acting on my bottle? My hand, my arm, correct. So in other words, me. What else? Frictional force, gravity. Okay. There's one more, and it's a force that you guys are not going to think about, but I'm going to show it to you again. Uh-oh. There we go. So let me see if I can get the book. Okay. There is one force you guys are not mentioning, and it's probably because you don't even realize that it's a force. The book pushing up. That is absolutely correct. Yes. The book is applying a force to the bottle. If the book wasn't applying a force to the bottle, what would happen? Seriously, Hanlon, that's you? You're a stupid person? That's the furthest thing from the truth. But that was a great answer. They're right. Now, if the book wasn't pushing up on the bottle, what would happen? And if you need another example to help, let me know. You guys see this all the time in commercials. Think of paper towel or toilet paper. No takers, huh? Well, if I were to take a wet paper towel and I were to put, let's say, a Post-it note on it, chances are nothing would happen. But what if I were to take a baseball and stick it on a wet paper towel? What would happen? It would go right through. The paper towel is not exerting enough force and it would drop. Think of a bowling ball on a pillow. Think of your head on a pillow. Your head is exerting more of a force on the pillow than your pillow is exerting on your head. Okay? And as a result, your head caves in to the pillow. Okay? The pillow dents and your head goes in. If you were to drop something heavy on a pillow, it would release and it would sink. If you were to place a piece of paper on a pillow, it would sit on top of the pillow with no problem. Okay, so when you're looking at something like what I just showed you with the book and the bottle, okay, if something is sitting on a surface and the surface is not giving way, then the surface is applying a force, okay? But in this particular case, the force that the bottle is applying on the surface is even to the force that the surface is applying on the bottle. That's why it's able to sit. If it wasn't able to sit because the bottle, let's say, was applying a greater force, then it would cave in. Okay, I hope that makes sense. If you were to look at a graph that represented constant speed, what would that graph look like? Any ideas? If you were representing a graph that showed constant speed, what would that graph look like? It would be linear. You're absolutely correct, Rosie. It would be a linear diagonal line. Okay. All right, guys, we're gonna stop for now. Okay, we've had 40 minutes, and I want you to just take some time to go over activities 84 and 86 if you haven't already done so. I know some of you already jumped on the ball. Oh, by the way, a couple of you may notice that you have a grade for activity 86, but you don't have an assignment turned in. And the reason for that is because there were 2 activity 86s. I had to recreate the activity and delete one, and it didn't delete in all the classes, and I didn't realize it. So some of you put it in the one that I had to delete. So I checked it, gave you the score for it, but I had to delete that column, which took out the assignment that was turned in. But if you turned it in, I gave you credit for it. Okay. So I hope you guys have an absolutely fabulous weekend. If you have any questions, by all means, please feel free to let me know. I'll stay around for a moment or two in case you have a question that you need to ask me, but I am going to end the stream. So enjoy your weekend, spend some time with your family, and I will see you on Monday. Bye.